So what we obtain is the power average has to be equal to 1/2 rho 0 C U 0 square, and then I have A over R to the cube, and I have 1 plus KA square, and I have what? KA and KR, right? And I have A over R to the cube. So I want to use 1R to eliminate this, because this is KA square. Then I want to use another A to eliminate that one. Okay? Then I have K square, and I have 1 over here. Right? Is it good expression? Or you want to have another expression? Okay, this is rho 0 C, and this is U 0 square. And the U 0 square is the square of the velocity.
Isn't it intensity? P is
Yeah. Yeah. Right. Your question is, what's the difference between intensity and the power? Okay? Okay, that's very excellent question. He said this is 1/2 real part PU is intensity. Right? So power has to be what? Intensity multiplied by what? Area. Huh? What's the area in this case? Okay, so area is 4 pi A square. Okay, you want to see the total power coming from the sphere that has an area of 4 pi A square. Okay, considering this, so we multiply this, because this is intensity. This is intensity, so I have to multiply this. And then taking care of these factors again, we will obtain what? 1/2 rho 0 C U 0 square and 1 plus K A square and KA square. Is it correct? A over R. Yeah. And then A over R square. Yeah. Okay. So it look like, how does it look like? This one look like when KA goes to infinity, it radiates as if it is in the far field, and in the near field, the radiation is not as efficient as we can see in the far field, right? Okay, this is what we get. Another representative radiation case would be trembling sphere. Okay. So let us do the very similar things to what we did for the breathing sphere from trembling. Sphere. Trembling sphere is a sphere but this is trembling in z direction with u0 exponential minus j omega t. Okay? And let's see, this is phi. Okay. And then this is theta. Okay, then this particle is supposed to be oscillating with the magnitude u0 and exponential minus j omega t. What about the boundary condition of this sphere? The boundary condition for breathing sphere was velocity at r equal a has to be u0 exponential j omega t, meaning that the breathing sphere is oscillating with the magnitude u0 oscillating in time exponential minus j omega t. Okay? But how about the boundary condition over here? In other words, how this fluid particle has to move in terms of velocity. u0 exponential j omega t, that is the velocity of this particle, right? But note that we are handling inviscid fluid, meaning that the particle can slip in tangential direction. Okay, for inviscid fluid, the only direction we can prescribe the boundary condition, or we can require the motion of fluid, is only in the direction normal to the surface, right? So this direction, and in this direction, the velocity in this direction has to be u0 cosine theta exponential minus j omega t. So this is the boundary condition. Okay? Right? So the problem we have is, okay, velocity in r direction, surface normal to the surface, to the trembling sphere, is u0 cosine theta exponential minus j omega t, and the governing equation governing wave equation has to be written in polar coordinate. That I cannot remember. Well, anybody who can remember the governing equation in polar coordinate? In other words, anybody can remember the Laplacian in polar coordinate? I respect him. So let's look at what was written in the text.